Okay, so one of the things I'm going to be doing during this section here, um, I'm going to be showing you a lot more video clips than I used to. Okay. Um, I mean, not that I don't know what I'm trying to teach you, because I mean, this is a very strange feeling for me. I feel like I'm a fairly smart person here, but sometimes the best way of me teaching you something is to find somebody else to teach you something. Just because I'm okay, but if I can find a video clip that does a better job, I'm going to do that, right? That would only be smart. So we're going to be watching a lot more video snippets than we have in the past. Just trying to explain these concepts. So, okay, let's get started here. Let's talk about EMR, and we'll see how far we can kind of get today. When I think of EMR, electromagnetic radiation, I think of this sort of picture right here, or maybe you guys have done this sort of thing in like grade 8 science, perhaps. It's been a while, where you learn about like all the different types of energy waves. Did you ever seen this picture before? I think it's 8th grade, yeah. So you're starting from like radio waves into microwaves into the infrared spectrum. This, when I think EMR, I intuitively think of light because really light is the only thing that as a person I have the ability to process, right? I don't have a body organ that can process radio waves. However, I do have a body organ that can process light waves. Those are my eyes, right? And from like a biology point of view, then there's like the rods and cones in your eyes, and however that sort of stuff works. I don't care about that so much, but light. You guys talk about that, right? Right. Okay. So I'm not a biologist, but I can relate to light because it's literally the only thing that I have the ability to sense. Right? I can't sense X-rays. I can't sense radio waves. I can't sense gamma radiation. Right? So when I think of EMR, I think of light. But I need for you guys to recognize that really it's part of a large spectrum of energy, right? And so the first thing I have written up there is I need you guys to be aware that when we call it the speed of light, yes, light travels that speed, but so does everything else. An X-ray travels 3 times 10 to the 8. A microwave travels 3 times 10 to the 8. Really, everything that's part of the spectrum travels the same speed, 3 times 10 to the 8. Okay. I have probably 3 main goals today. Goal number 1, I need to help you guys relearn some of the details about all of the sorts of EMR spectrums. That's topic 1. Topic 2, we need to talk about how physicists discovered the speed of light and how they calculated that value, because you guys should be able to replicate that as well. Okay. And then the third thing we're going to talk about is what I just showed you with the symbol here, the idea that even though all of this stuff is a wave and it's an energy spectrum, it also can behave as a particle as well. And we're going to talk about wave-particle duality briefly. So those are kind of my 3 main goals. Revisit the spectrum all the way from your radio down to your gamma radiation, topic 1. 2, let's talk about... I already blanked on this. What did I just say topic 2 was? What did I just say? Oh, how we calculated the speed of light. Yes, sorry, we need to know how. So we're actually going to revisit 3 or 4 different scientists' contributions. And you guys should know the scientists' names and what they did, because that could come up. And then topic 3, we'll talk about how light can be a wave or a particle. Sound good? Okay, so let me jump around a little bit here. Let me jump. Can you guys find these slides right here? I'm going to go in a slightly different order than I had originally designed this, but I think this will make more sense. So let's start by doing a basic review of grade 8 science and talk about all the different types of waves on the electromagnetic spectrum. Okay, so starting at like the far end of the spectrum, you've got your low frequency AC waves and like your radio waves. Okay. Now, before I get into this, let's do a quick recap lesson on how the waves work in terms of terminology. If something fits a wave format, it looks something like this. Right. For you guys in my math class, in our next unit, we're going to talk about how this is a sine function. We'll actually learn about how it relates to trigonometry. For a wave like this, do you guys remember the definition of amplitude? What's an amplitude? What was that? Yeah, like the height. So like from here to here, or from here to here, that would be an amplitude. Okay. So on a wave, does anybody know what an amplitude determines? Yeah, not how much energy, how loud it might be, for example. Okay, like how strong the signal might be. Okay, if you had a larger amplitude wave, that might be in terms of like its signal strength. It actually isn't its energy. We'll talk about energy in a little while. Um, but like as for a sound wave, if you had a taller amplitude sound wave, it might be louder. Okay. Okay. Another terminology we need to know is this distance from here to here. Does anybody remember what we call the distance between crests? It actually has a mathematical symbol. We use T. It's the period, yeah. The distance between the crest or the trough is known as the period. You guys hopefully remember period from a previous unit. Period is like how long it takes for something to repeat itself. Okay. Now, when it comes to your radio waves and your low frequency AC, they have very long wavelengths, which means the distance from here to here is like when you use one of these photos. Don't flip back. I'll just find one for us to work with. Where is one here? There we go. Radio waves. It's a very, very long distance between this one to this one right here. Does that make sense? So this has a very like this one has a period that is a large amount of period. Okay. However, we had another formula we learned, which is that period is equal to 1 divided by frequency. Do you guys recall that formula? If this has a very, very large amount of period, what does that mean about the frequency? Very low, yeah. So radio waves actually have about the lowest frequency we have. They happen very infrequently. Right? They don't have a high frequency. Conversely, over here, your X-rays and your gamma rays, the distance in terms of like nanometers between crests is actually very small. So this would actually have a period that is very low, which means that it has a very high frequency. Does that make sense? So I just want to make sure we're clear on the terminology here. Thanks. Okay, so low frequency AC and radio and radar type things, they have a very long amount of distance between each other, but it means they have low frequency. Okay, we'll talk later, but frequency is actually related to energy. Okay, it's not the height of the wave that's necessarily related to the energy. It's the fact that it doesn't happen very often. The distance between them is low. So pretty much any device that like has random static on it is actually emitting out some sort of EMR wave. However, these things are so large in terms of like their distance between each other, literally it will like go around a person, right? Like this distance right here could be like 7 meters, right? And so they are not harmful to people whatsoever because the wave will literally just pass right around you. You know what I'm saying there? Radio, like if you still have a radio in your car. I didn't know this. You guys still have radios in your car, or they don't get rid of them now? Cassette player. 960 AM, like if you were on like an AM dial, that's actually how many kilohertz your frequency is. That's how much kilohertz your frequency is. What's a kilo as a prefix? Times 10 to the 3. So this would be a times 10 to the 3 as a frequency. Okay. I want to flip to the next slide here. Microwaves actually work on 2.4 gigahertz. What's a giga prefix? Giga is times 10 to the 9. Okay, so let me see if I can try to relate this here. Frequency, even though your radio waves are a kilohertz, which is still very infrequent, as we get up to, like, say, our microwaves, we're now up to gigahertz, which means that when we get to light and to cosmic radiation and gamma radiation, that's going to be even higher in terms of its frequency. It might be to the power of 15 or 17 or 22. Does that make sense? So if you wanted to, maybe you guys should actually find this diagram way at the beginning here. Just as like a frame of reference, the frequency as like a general idea here. Radio waves would be like a times 10 to the 3. hertz, and microwaves would be a times 10 to the 9 hertz. And as you go further and further across, it's only getting more and more frequent. Does that make sense? What's a hertz again? How many times it oscillates per second. Yeah, it's based on its speed, right? So as it goes up and down and up and down and up and down, this thing would oscillate 1,000 times in a second. Follow that? A radio wave oscillates 1,000 times a second. A microwave would then oscillate like 1,000,000,000 times a second. Is that right? 9 zeros for 1,000,000,000? So gamma rays must oscillate like 1,000,000,000,000,000,000 times per second, right? I don't even know what that number would be, right? But make it times 10 to the something large. So far so good? Okay, let me talk some more about these ones here then. So microwaves are next. Microwaves have more energy due to their higher frequency, and it's actually set to vibrate at the natural frequency at water. Do you guys recall in the unit on talking about like period and stuff? I gave the example of me pushing Kinsey on the swing, and as you push her on the swing, if you push her with just the right frequency, where you push her at the right time, she keeps going further and further and further. That's actually what microwaves do. Microwaves are set to oscillate at a frequency of 2.4 gigahertz, which is the natural resonant frequency of water. And what that ends up doing is it makes the water molecules start vibrating a little bit more, and a little bit more, and a little bit more. Well, what is heat? Isn't heat a measure of kinetic energy, a measure of particles that are vibrating? And so essentially what the microwave does is it causes those water particles to move more and more and more, right? Thereby heating up your food. Actually quite brilliant, all things considered. So I think this is worth noting here. Even though they're called microwaves, you know how micro is like, yeah. Yeah, it still will, because there's probably some water content in it, right? Right. But I mean, even there's water vapor in the air around it, right? Right. I mean, even think human body. You might think, the human body is 70% water, right? So even if you're heating up a piece of meat, there's still got to be some sort of water in it. I don't know about if you're like talking like maybe beef jerky that's been completely dried out, but probably. Here's the thing: is even the non-water molecules might still be able to vibrate, though, right? But like the microwave has been set so that the water molecules are what naturally vibrate best. Yeah, exactly right. Yeah, you've heard that before, right? You actually want to put something in there, otherwise it's not doing what it's supposed to do. Okay, here's the point I wanted to make here. We call them microwaves. You know how micro is a small unit of measurement? Okay. They are not small though. Microwaves are actually your second largest type of waves in terms of length, right? Your radio waves are the longest distance. Microwaves are actually the second smallest. However, they called them micro because it's better than radio waves. So the frequency increases, the wavelengths get smaller. They're not the smallest ones we have, but they are smaller than radio waves. You know what I'm saying here? So it might have been poorly chosen to call them micro because these are a large distance between each other. These microwaves right here are still a very large distance between each other, but they're smaller than over here. So that's how they got called microwaves. Really, where should we have put microwaves? Yeah, like that should have been a microwave, and this should have been a nanowave, and this should have been a femto wave. That would have been smarter to call them that. But anyway, so micro gets to go over here. All right. Infrared is next. Infrared, you guys probably have done this stuff before here. Infrared is like where they use them in TV remote controls. You guys know the little sensor bar they put in front there? A TV runs on infrared. They also use IR goggles to like SEAL Team 6 that goes in and tries to assassinate like some bad terrorist guy, and they put on like those night vision goggles. They're using like IR goggles. You guys ever heard of that before? Infrared. So that's infrared. Next on the spectrum is visible light. Have you guys heard the acronym Roy G. Biv at some point before in your life? Red, orange, yellow, green, blue, indigo, violet. Okay, this is the only type of radiation, electromagnetic radiation, that you actually have the ability to perceive. Right? I can't feel radio waves hitting me. I guarantee you, radio waves are hitting you right now. Right? I mean, not only that, but microwaves are hitting you because your cell phone operates on a microwave frequency. And so you're probably being bombarded currently with all sorts of radiation, but you can't feel that stuff because it's way too wide. But our eyes have the ability to perceive natural light. So, in terms of numbers here, we'll start using the math a little bit later in this unit. But red is the lowest frequency, and violet is the highest frequency. So in terms of like your wavelength right here, as it gets like shorter and shorter, I'm not drawing this very well. Over here is your red. Your red is the furthest apart, and your violet is like the shortest apart. So it means that purple has more energy than red does, essentially. I have missed something after visible light. Yeah, after violet is supposed to be your ultraviolet UV, and somehow I've missed a slide on here. What do you guys know about ultraviolet radiation? What does it do? Skin cancer is the most common thing people will bring up, yeah. The two most common ways you'll have encountered UV radiation is the sun provides UV radiation. The two best ways for us to block UV radiation from the sun is to wear sunblock, or we have an ozone layer around the Earth, which is supposed to absorb the ultraviolet spectrum, ideally, which is why it's so important not to let our ozone layer deplete because it's causing problems. The other place you might have seen UV radiation is black lights. Black lights operate on the UV spectrum as well. No, we're still not to the point of being to that like high enough energy yet, right? Well, I mean, like natural light still is not dangerous, right? If light hits me, I'm not worried about that sort of problem, right? Now, if you were to expose yourself in long doses, maybe to black lights, perhaps, but like we're not talking a huge amount, right? I guess I shouldn't say like straight up no, right? But we're getting to that area there, right? The next one, though, this is where it starts getting to the point where the human body starts having problems because now these wavelengths are starting to penetrate through skin, through flesh and bone. X-rays basically go through everything in your body except for bone and teeth, which is why we use X-rays then to get pictures of bones and teeth because it'll pass through your flesh but not your bones. Right? Your bones are too dense. So X-rays, again, safe in low doses, but I mean, if you're constantly being exposed to X-rays, you want to, use the lead protection to try to prevent, especially like in pregnant females, birth defects would be a good example there too. So, gamma rays are not just science fiction, even though like Bruce Banner, the Hulk, if you watch Marvel movies, is based on gamma rays. Those actually are true. Like gamma rays do exist. They won't turn you into a freakish green monster, but there is such a thing as gamma rays. We use them on chemo. So if someone's going through chemo because they have cancer, we use gamma radiation because it is very, very fine now in terms of like radio waves, microwaves, visible light, X-rays, gamma rays. We're talking like the smallest amount of wavelength, the highest frequency, and with that super high frequency comes super high energy we can use to try to target the cancer cells. Does that make sense? So we use them for chemo. There's actually one further that we usually skip on a lot of diagrams. Cosmic radiation is kind of the highest thing you can get to in terms of its frequency. These would be super dangerous in high doses, but here's the cool thing. Natural cosmic rays are so small they pass through all matter. So like they would actually phase through the Earth itself. They are so small in terms of their wavelength. And this is the sort of thing that I can't even explain to you about because I don't know anything about it. If I did, I'd be writing a PhD on it because like only a few people in the world really understand cosmic radiation. So that's what makes this cool in my opinion. So okay, topic 1. Do you guys recall the spectrum? You've heard that before? I need you to know the order at the very least and roughly some rough ideas about where their frequencies are at. So here's how I remember it. I remember that the 960 or 1040 on my radio station is a kilohertz. So I remember that it's 960 kilohertz in terms of radio, and then I can kind of work my way from there. The other one that I memorize is in the visible light spectrum. I threw some numbers in there for visible light at some point. And we're going to use these numbers when we get to the math section later. Visible light has a wavelength, not a frequency, but a wavelength of like a couple of hundred nanometers. Okay, so I use those as kind of like a reference point, just so you have an idea of about where things would fit. Does that help? Okay, so there's topic 1. Okay, let's do topic 2. Let's talk about a bunch of scientists now. So let me jump back a little ways here. Is that okay so far? Oh, like not topic 2 notes, but like, you know how I said I had 3 main goals today? Goal 1, remind you of the electromagnetic spectrum. That should have been our easiest part here. Okay, topic part 2 now. I need to talk about a bunch of scientists who helped contribute to this. So, okay, let me start by explaining to you what we currently believe about electromagnetic radiation, and then I'll work backwards and talk to you about how we got to this point. Do you guys recall the universal wave equation listed there? It's V equals frequency times wavelength. That was the universal wave equation. We used that before. We're going to use that one again in this new unit. The good news is that the velocity is always the same thing, speed of light. So really what you're left with is a reciprocal relationship where as the frequency goes up, the wavelength would have to go down. Right? As your frequency goes up and you get to something like, say, gamma radiation, well, the length must be lower. Right? As one goes up, the other goes down, or as this one goes down, this one has to go up. Right? So that's the formula that we can use when we get to the math part here. Okay. Here's the other thing I need to talk about is the reason how this exists. And it's all based on accelerating charges. If you want to highlight this, this is kind of the important thing. I don't know that I can explain the why, but I know I can definitely explain the what. Okay. If you have an accelerating charge, think of Ørsted. Do you guys remember Ørsted's first experiment? He had a wire, and that was his first left-hand rule. As he had a charge going through a wire, it caused a magnetic field to go around him. Does that make sense? Now, for the life of me, I don't know why that happens. I just know that it happens. You know what I'm saying here? So, and I think Ørsted's probably in the same sort of thing there too, is he was able to recognize that electricity caused magnetism, but he didn't really know why. But think this through then. If you have an accelerating charge, like you say you just have electrons running through a wire, wouldn't that then cause a magnetic field? However, another guy we learned about, Faraday, discovered that if you were to take your solenoid and take your magnet and put the magnet into the solenoid, didn't that make electricity? You guys remember that? So really, you have this interlapping set of things where electricity creates magnetism, but magnetism creates electricity, but then electricity creates magnetism, but then magnetism creates electricity. And that's basically what we believe happens in EMR, is you have these alternating perpendicular magnetic and electric fields. So they don't actually occur just in the X direction, they actually occur in the X, Y, and Z direction. Right here, you might have a magnetic field. And this is the magnetic wave basically going up and down. But as a magnetic wave gets produced, we learn that magnetism makes electricity. And so then it also makes itself an electric field. But then the electric one remakes a new magnetic one. And so the belief here is that when you actually see light or an X-ray or whatever it happens to be, there's actually stuff happening in 3 dimensions. In one dimension, you have the magnetic field. In the second dimension, you have an electric field. And in the third dimension, it's the direction of travel. And so as this thing travels this way, in this direction is one field, and in this direction is a second field. And that's where we get the name electromagnetic spectrum. Minus the why, does the what make sense? The idea that we've learned electricity can produce a magnetic field. And we've also learned that a magnetic field can produce electricity. So that's what we believe. It's like it's self-perpetuating almost. Right? So here's like the 2 scientists that we've talked about before. Right? Ørsted figured out that current makes magnetic fields. Faraday discovered that magnetic fields can produce a current. Right? So the first scientist I need you guys to know about in this unit, his name is James Maxwell. And in 1865, he basically theorized that these things must be perpetuating each other. Magnetic creates electric, which creates magnetic, which creates electric. Right? And that's basically the radiation we have. Oh, that reminds me. I want to talk for a minute about the word radiation. Radiation kind of gets a bad vibe. Because when you hear the word radiation, you think, oh my goodness, I'm getting cancer, I'm going to die, right? But that's not necessarily true. Some forms of electromagnetic radiation are very dangerous, right? Your gamma rays, your X-rays, your cosmic rays, right? Even ultraviolet can cause cancer, right? But not all forms of radiation are dangerous in the same way, right? Like, I'm not afraid of visible light, right? Visible light has not hurt anybody to the best of my knowledge. Actually, that's not true. There are some people who actually can't be outside in the sun, but that's different stuff, right? But like, currently you're being bombarded with radio waves and microwaves. We're not afraid of those, but that is still radiation. Does that make sense under the term we're using there? So I should point that out. Oh, anyways, Maxwell puts together his theory then of electromagnetism. The board is not working today. He puts together his theory of electromagnetism, and here are his 6 kind of conjectures at the end there. So first thing, he discovered that EMR gets produced whenever a charge is accelerating. This is the key. First, you have to have a charge being accelerated. Because what does a moving electric charge do? Creates a magnetic field. And the magnetic field creates an electric field. So pause for a second here. Visible light's coming out of those light bulbs. Why? What's happening in those light bulbs? Well, somewhere up in there there's a filament, and it's being attached to some sort of electricity, and it is accelerating an electron. And as that electron accelerates, either like in a loop or back and forth side to side, that accelerated electron is emitting out a frequency. And that frequency just happens to be set so that it creates visible light. Right? Your cell phone has very, very similar sort of concepts to it, only its frequency is set to the microwave region. And so therefore it emits a signal that we can't see, but that your cell phone can pick up instead, right? If we were to set the frequency to be so fast, it may end up creating X-rays. If we set it to be a little bit slower, visible light, even slower than that, may end up being like radio waves. What was that? Oh. Does that make sense to you guys? So there's Maxwell's first postulate. You have to have an accelerated charge. Okay. And then the second one is that, well, the frequency with which the charge moves, that's what makes your EMR. So depending on how fast your charge accelerates back and forth, its frequency, that sets the sort of EMR you get. So our light bulbs are producing visible light. I have black light bulbs. Would the charge on would the electrons on the black light bulbs be going faster or slower than a regular light bulb? Why faster? Because ultraviolet has a slightly higher frequency than regular light. So therefore, the electrons must be oscillating back and forth faster in the black light bulb, thereby emitting out its wave. So, other things here, Maxwell figured that it must be traveling all the speed of light. They are perpendicular to each other and also perpendicular to the wave's travel, which is basically this picture here. One goes in the Y direction, one goes in the Z direction, and the direction of travel is the X direction. He figured they must actually be in 3 dimensions. And there's other postulates here. EMR is going to behave like other waves. So we're going to spend the next 3 lessons, we're going to talk about some of the things that EMR can do. The 3 main things it can do is it can reflect, it can bounce off of a surface, it can refract. Does anybody know what refract means? Sure, I get what you did with your hands. Can you put that into words? Okay, we have a very, very technical word for that. We say that it bends. That's not actually that technical. But I get exactly what you said, though, yeah. So we can actually reflect light, we can bend light, and then we're going to spend the last day talking about how they can do things like interfere with each other, and another word called diffraction. So those are our next 3 topics, by the way. How it reflects, how it refracts, how it diffracts and interferes with itself. Anyways. And then the last thing is that the wave equation then, the speed of light, which is your velocity, and frequency and wavelength, that would then apply. So anyways, that was Maxwell's contribution. He writes this paper. He then came up with some equations, and this is another one of those things where I can memorize these equations if I had to. I have no idea how they work. So I just threw them on here just so that you could see the famous Maxwell equations. For you two who are in calculus, there's actually one thing I do actually understand. This right here, that's a derivative. Right? It's a different symbol, but this is the change in the magnetic field compared to time. Right? This is like dy over dx. This is the change in the magnetic field with respect to time, which kind of makes sense, right? As you have a changing magnetic field, it should have some sort of, this must be an electrical field, I'm guessing. So, that's about as much as I know about these things. Okay, another scientist, Heinrich Hertz. So it was, I think, 65 that Maxwell put out his famous paper postulating all these ideas. Hertz did an experiment to try to confirm these theories on EMR. And rather than me try to explain Hertz's experiment, here's a YouTube video that will hopefully help visualize it. So I'll talk about it after I show you the video. Hopefully this works.
Around 1818, the brilliant scientist James Clerk Maxwell developed the mathematical theory of electromagnetism. His theory predicts that electromagnetic waves propagate through space at the speed of light. Many other scientists of the time were trying to prove experimentally the existence of these waves. In 1887, Heinrich Hertz, a German physicist, designed a series of brilliant experiments to demonstrate Maxwell's hypothesis. Heinrich's equipment was simple: a spark generator coupled to an antenna and a metallic ring set at some distance apart. Heinrich proposed that the electromagnetic waves generated at the antenna will travel through space, and if Maxwell...
Okay, pause for a second here. I know it's not the greatest language, but the order and the sequencing of the video work here. What he's really doing is he's causing, using his voltage right here, he's causing a spark to oscillate back and forth between these two little poles right here, right? And as we just talked about here, the idea should be then is whatever frequency the spark oscillates back and forth at, that should create the same matching sort of EMR wave, right? Well, he set that up over here, but he also set up over here a receiver, right? And in the same sort of way that your cell phone is a receiver, somewhere else is sending out a signal. Somewhere out over here, it's now receiving that signal. And so this was like the first time that a radio wave was intentionally sent, transmitted, and received.
His theory was correct. They would induce a current in the ring, and a spark will appear in the ring gap. In this video, we make a simplified version of this famous experiment.
So the reason why I like this one here, I don't have the apparatus to do this, but we can watch them do an experiment here.
And we will obtain that pulse with a lighter like this. Here we have one that we have modified for our purposes. Let's open the lighter. Here it is. This is a piezoelectric element that produces a pulse of several thousand volts. There are these two wires that come from the piezoelectric, and we have connected these two wires in order to...
So normally the way a lighter works is that it just shoots a spark, and then the spark will light the lighter fluid. He's set this up here so that he can now visibly see the spark going in between the two alligator clips, right? You're seeing an electron jump, right?
To replicate Hertz's experiment, we have the spark generator connected to these two wires, and the electromagnetic waves will travel through the receiving antenna. Here we have a neon lamp connected to the antenna, and when the spark is produced here, the neon lamp will glow.
So idea is that we're going to have the spark go on the first ones. It should send a wave to the second ones, and it should complete the circuit so that you can actually see the neon lamp turning on there. Okay, let me just pause for a second there. So what he did is he shoots the lighter off of the lighter, right? And it shoots a spark through a circuit, right? And he actually, I mean, you know how we had these two things really close to each other? You could see the spark shoot, right? Well, that's an accelerated electron. Well, the accelerated electron is going to jump from here to here. As it finishes off this loop right here, though, an accelerated electron with whatever frequency that it's running at should be able to set off a wave. The wave goes over to here, and it actually manages to complete this circuit over here instead. And so you're actually able to see a receiver and a transmitter set up here. You guys can see the light bulb flashing, right? Are you guys able to see the little spark across this one right here? Spark's going across this one, but the further one right over here, it's actually lighting up as well. So this is essentially what Hertz did back in whatever it was, 18 something.
A more powerful arrangement. We are using now high voltage power supply.
So I'm not trying this.
Power supply following the link to the video that is now on the screen.
Yeah, I wasn't trying it.
This power supply outputs several thousand volts. The output
Several thousand volts.
supply is connected to this capacitor. The capacitor stores the energy, and the spark will be more powerful in called.
So he's basically just making it bigger so you can see it better now. All right. So do you guys get the concept here? All right. Now, so long as you can tell me the what, that's important. The why's a lot harder, right? I'm not even sure I fully wrap my head around everything. I get the idea of how, okay, an accelerated charge should create an magnetic field, which should make an electric field. It shoots that across. I'm not really fully sure I get how it makes the light bulb light up, but what it seems to end up doing is it causes the same spark that came across here to cause an electric field. Right? There must be some sort of electric field or magnetic field changing in this sphere right here, pushing the electrons through the wire. Just like we saw when you guys took the solenoid and you put the magnet into or out of the solenoid, it caused electron movement, right? So there must be electron movement happening over here, and again, we have action at a distance. Right? And I mean, really, this is what happens in any sort of signal, a radio signal, even the light is really doing the same sort of thing here, right? Got some sort of oscillating charge. So that's essentially the Hertz experiment. Make sense? Okay, let's move forward because I'm running out of time today. Next, I want to show you a video on some scientists who helped figure out the speed of light.
Assuming you are sitting in an almost like classroom, it took that light about 10 nanoseconds to reach you. In turn, for you to have known that the light has reached you, it took about 200 milliseconds. Congratulations, you were about 20 million times slower. As you can see, the speed of light is so fast that it precedes our immediate perception. So how do people measure it? More specifically, how did people before the 20th century try to measure it? Did they get close to the real answer? During Galileo's time, many believed that the speed of light was infinite. In fact, they had no reason not to believe that. Galileo, being Galileo, disagreed. He tried an experiment in which he and another person each took a shuttered lantern and walked a mile apart. The rule was that as soon as one of them flashed his lantern, the other would flash back. And Galileo would simply divide the distance by the time. He found that the speed of light was at least 10 times greater than the speed of sound, or 3.4 kilometers per second. Little did they know, they did more to measure the reaction time and the speed of their arms.
So the hardest part was when to actually light the lantern, right?
Then he added avoiding trouble with the Catholic Church. During the 1670s, inspired by Galileo's discovery of Jupiter's moon and his belief in the finite speed of light, Danish astronomer Ole Romer made another attempt at measuring the speed of light. Initially, Romer was trying to predict the orbital times of Jupiter's moon Io. To his frustration, however, he discovered that Io was not orbiting strictly on schedule. Romer simply did not accept the possibility that Zeus might have been keeping Io late from his telescopes. He noticed that Io was ahead schedule when the Earth was closer to Jupiter and behind schedule when Earth was farther away from Jupiter. Romer deduced that the irregularities in Io's orbit must have been due to this finite speed of light. Based on careful observations, his data implied that the speed of light was about 300,000 kilometers per second.
Oh, what, a kilometers times 10 to the 3? Add 3 more zeros on there. That's almost 3 times 10 to the 8, right?
Equally, Louis Fizeau produced another measurement for the speed of light. Fizeau shone a beam of light through a rapidly rotating tooth wheel into a mirror 5 miles away. The mirror reflected the same beam of light back through the rotating wheel. By varying the wheel's rotational speed, Fizeau could see when exactly the light is not had enough time to be reflected back through the same gap in the wheel. His speed of light was about 313,300 kilometers per second.
A little bit too high.
In France, 1862, the young Foucault modified Fizeau's experiment and made a more accurate measurement of 299,796 kilometers per second.
Okay, I just want to go back to this idea right here. I don't remember the guy's name. It's the third one on the list that you have sitting there, but he came up with this brilliant idea. And the guy we're going to talk about on the next slide modified it. He shot light. How's it supposed to work here? The light's supposed to bounce here. It's supposed to go to the mirror, bounce off the mirror, and come back again. That's kind of the basic concept. But in order for the light to go through, he's got like this spinning wheel with like spokes protruding through the edge of it, right? And so light may or may not make it through the gap, right? Because it's spinning so much that as it spins, the light may make it through, right? Well, then it's going to travel all the way there, all the way back, but in the meantime, the wheel has spun, whatever the right verb is there, adjective. Anyways, right? And as it comes back again, it may end up passing through a crack again, or it may end up hitting one of the spokes. And so what the guy did is he manipulated the amount of rotation of this thing and tried to use that to figure out exactly how fast the speed of light was. That's kind of the basic concept. I want to show you now the guy that you need to be aware of his name, which should be on our next slide here. Okay, so this is the Michelson experiment, and I more or less just stole this entire thing out of your textbook. So I even wrote down right here. Can you guys read through chapter 13.2 at some point? Because you might find that you learn a little bit more than my explanation. But here's the experiment you need to be aware of. Okay, Michelson had this brilliant idea. He didn't use like a rotating like teeth. Do you have the slide? You have the slide? Okay. So he shoots light from the top of Mount Wilson, and he hits a mirror. Then it travels, and I don't know how he pulls this off, but it travels 35 kilometers. So like light is traveling like most of the way to Lethbridge. Hits a mirror, travels all the rest of the way back again, hits that same mirror, and then comes in his telescope. Okay. Now, but here's the thing though. He rotates this mirror. And as he rotates this mirror, as the light comes in, hits the mirror and bounces back down, in the meantime, the mirror has slightly rotated. Does that make sense? And so unless the mirror is right back in the exact same orientation, as the light comes back on its return journey, if the mirror happens to be like, if the disc happens to be like this, it would hit here and it would go up, say, that direction, and he wouldn't be able to notice the light, right? So he tweaks the rotational speed of this thing here until the light comes in, bounces down, comes back up, and discovers. And he realizes that the lowest rotational speed he can get away with was 533 hertz, or 32,000 revolutions per minute. When that was occurring, he was able to see the light come in here, come back down, bounce back up again, and in the meantime, what would have happened is this thing would have rotated 1/8 of a rotation. Does that make sense? It's going to come in, hit. As soon as it hits, the thing is still moving. It'll rotate 1 panel's worth. It'll have gone down and back up again and be able to go there. And so here's the math. He does period as 1 over frequency, and he calculates the amount of time that it took for his wheel to rotate all the way around once. Except he knows that the wheel didn't rotate once. It actually rotated like only 1/8. It only rotated from here 1 little flip. So he then, to find his time, he divided by 8. So basically he knew the amount of time it took for the light to go from here back up to here. He then made sure it was a super large amount of distance, which was this number right here is 70000 meters. Anyone figure out how that number just showed up there randomly? It was 35 kilometers. So 35 kilometers is 35000 times by 2 because the light had to go there and back. Long story short, he finally divides them together, and he gets what is now universally known as the speed of light. We round it to 3.0 times 10 to the 8, but it's probably closer to 2.989 something in there. That's the discovered speed of light. Does that make kind of sense how the experiment worked? Okay. So there's actually two main ways then to detect electromagnetic radiation. Here's the two. Directly, if EMR is unimpeded, just like in the Hertz experiment, we can detect electromagnetic radiation by setting up a transmitter, setting up a receiver, and literally just having the transmitter transmit to the receiver, right? Think your cell phone, right? Or you can do the reflection or transmitted sort of idea. And I want to show you a brief clip off of the Big Bang Theory now, which kind of has a very similar concept. You guys watch Big Bang Theory? This is from like seasons ago, before Leonard and Penny started dating. We'll touch you there. Let's pause there. Okay, so to explain their experiment, very similar to the Michelson experiment, a little different. Rather than it being 70 kilometers of total distance travel, they're firing it to the moon and back, right? It's about 2.5 seconds to fire light, or any really wave, from Earth to the moon and back, right? But really, I mean, that's the same sort of premise, right? Is that you'd calculate the distance from here to the moon. We know the speed that it's supposed to take. Based on those two numbers, velocity is distance over time, you should then be able to calculate the 2.5 seconds. Does that make sense? So that would be another way of, like I had on my slide right here, this would be a way of being able to indirectly measure EMR, is because it was able to be reflected. Right? Apollo 11, they put a mirror on the surface of the moon. As long as you can hit it with your laser, you can basically, as Leonard was saying there, that's probably the most definitive way of proving that we've actually been on the moon. Right? You know, those skeptics who are like, nah, they never landed on the moon. This is actually a way that we can prove it. No, there's a reflective surface on the moon that's transmitting the light back. Anyways, okay, moving forward. So I'm really running out of time here. My first two objectives: one, a review of EMR. You guys feel comfortable with that well enough? Two, hopefully now you feel like you know a little bit about how scientists got to the point of knowing what the speed of EMR was. The last thing I want to do is it's actually good that I put it last. Let me just talk through a couple of things here. I have a video here that I don't nearly have enough time for. But if you guys get a moment on my website, I've posted all of the video links that I normally would use. If you guys get a moment, maybe watch this one. It's a video basically just talking to you about all of the different parts of the EMR spectrum. It's about half an hour, so if you have some free time, put it on in the background while you're working. Okay, the last thing I want to talk about then is the scientific method and the idea that scientists are still working on trying to figure out exactly what's up with light and how it works as a wave. Here is basically the two historic models of light. They either thought it was a particle or a wave. And right now, the current theory is that it's both, and it operates as either a particle or as a wave, depending on which one's more useful at the time. I love this this picture right here. Can you guys see how it says P-A-R-T-I-C-L-E? Can you see that? But then it also goes like W-A-V-E. Yeah. So we are. Can you see it now? Life is a particle. Light is a wave. We're going to spend a whole topic on this in topic 7. So that's why I feel like I can rush through this because I'm going to revisit this again at the end of the unit. But let me give you the Cliff Notes version. Okay? Isaac Newton was such a living legend that for the longest time, he thought that light was a particle and nobody disagreed with him because no one wanted to argue with the Sir Isaac Newton chair at Cambridge. And so he basically thought light was a particle, and here was his evidence. He thought, well, light travels in straight lines. If I were to shoot a gun, it more or less travels in a straight line, ignoring gravity, right? Light can be reflected, means it bounces off something. Light can travel through a vacuum, because literally there needs to be no medium for it to travel through. That was Newton's idea. It looks like he was right. But after Newton's death, some scientists started working on the idea of light being a wave. And I have, until Newton's death, people wouldn't actually try to argue with Newton because he's the Isaac Newton, right? So here are the two people I want to talk about. We'll do this more later. Grimaldi showed that light could actually diffract through openings. And Poisson, he actually predicted that light should not be able to refract around a disk, but it actually did. Okay, let me see if I can explain this concept here. No, I'm rushing. Here's a light bulb. He sets up an object right here, and he shines the light towards it. Well, a shadow should then appear over here, right? If I put my hand in the way right here, a shadow shows up behind it, right? Well, what this guy discovered is that actually, right in the middle of the shadow, there was light again, which just makes no sense whatsoever. It's like, how is it possible? Here's the light. The light is supposed to hit the object, so like it's light up here, it's light down here. This right here should have been your shadow. Dead center middle of the shadow was a light spot. This meant that light had the ability to diffract and actually bend around. Waves can bend, not particles. And so this is something I find really cool. Poisson predicted that light should not be able to diffract. So when Arago discovered this, he made fun of his buddy by naming it after him. Basically like punking the guy, saying, you were wrong, so for all of history, we're going to remember your incorrect mistake. Okay, anyways, I'll call her quits here. You guys can read through the rest of the slides. We're actually going to talk about this whole idea of light being a photon. So to kind of end class, we heard photons of light on the symbol. The idea that light can be a particle, that's what we actually could hear. And Einstein only figured this out back in 1905, which is super recent. So, okay, tomorrow you guys will watch video 2. I'll talk to you guys on Friday, and we'll kind of pick up the pieces from there. Okay, sweet. Thanks, guys.